Welcome to Episode 2 of Module 2 in the Mastering AI/ML series, Data Types, Structured, Unstructured, and everything in between. The type of data you use dictates the algorithms, cleaning methods, and models that will be effective. This program is brought to you by the Series of Thoughts team and Technovative AI.
Not all data is created equal. From spreadsheets of sales figures to a stream of sensor readings, the kind of data you work with determines almost everything about how you can use it in AI. Before anything else, ask yourself, what type of data am I working with? This video will map out the full taxonomy of data types in modern ML, focusing on 4 main categories: structured data, unstructured data, semi-structured data, and time series and streaming data. Knowing the type is the key to unlocking the correct machine learning approach. The data type is the first question in any ML project because it creates a cascade effect. It defines the raw representation, dictates pre-processing, constrains algorithm selection, and ultimately informs the model architecture. Starting with the wrong assumption can invalidate weeks of work. Every dataset falls into one of these 4 categories or is a hybrid. Structured data involves spreadsheets and tables. Unstructured data includes images and text. Semi-structured data is found in JSON and XML. Time series data involves temporal patterns from sensor readings and streams. Our first data type is structured data. This data lives in rows and columns with a well-defined schema, making it the most mature and widely understood format in the industry. Structured data is characterized by organization into rows and columns, fixed data types per column, and an enforced schema. Common sources include SQL databases, CSV files, Excel, and enterprise systems like ERP and CRM. Structured data is the native format for classical machine learning. Common algorithms include tree-based models like random forest and XGBoost, linear and logistic regression for interpretable baselines, and clustering/dimensionality reduction techniques like k-means and PCA. A structured data preprocessing checklist includes handling missing values, encoding categorical features appropriately, scaling numerical features for distance-based algorithms, and addressing data leakage and skew before training. Next is unstructured data, which has no predefined schema or row-column organization. This is the dominant format of the real world, and the primary reason deep learning exists. Unstructured data carries meaning in patterns, not named columns. Categories include images and video, audio, raw text, and binary files. Each requires a representation layer to process the raw data effectively. Classical ML requires a fixed-length numeric vector input, which unstructured data lacks. Feature extraction is essential to create a dense, fixed-size representation. Strategies include handcrafted features, learned embeddings using models like CNNs and transformers, and leveraging pre-trained models for transfer learning. Deep learning architectures are key for unstructured data. Convolutional neural networks are designed for spatial data. Transformers for text model long-range dependencies. Audio and speech models often reframe waveforms as 2D spectrograms for CNN architectures. Semi-structured data is the middle ground. It includes organizational markers and hierarchical tags but lacks a rigid tabular schema. This format is dominant in modern APIs, web services, and NoSQL systems. Semi-structured data has self-describing tags, hierarchical nesting, and flexible schema. However, it lacks enforced column types, fixed field presence, and direct compatibility with row-based ML algorithms. Common formats include JSON, XML, HTML, and API responses. Semi-structured data needs to be processed through a 2-phase pipeline: parse, validate, and extract structured features, then apply the machine learning method of choice on the flattened, typed result. Real-world semi-structured data presents challenges such as schema drift, deeply nested structures requiring recursive parsing, mixed content that needs separate processing paths, and the need for distributed parsing at high volumes. Our final data type is time series and streaming data. This data is uniquely defined because order matters. The temporal sequence is the signal itself, not just metadata. Time series data is fundamentally different because shuffling destroys the signal. Key properties include temporal ordering, autocorrelation, seasonality, non-stationarity, and irregular irregular sampling. Common time series sources in production include IoT and sensor telemetry with high frequency, financial market tick data characterized by extreme non-stationarity, server metrics for anomaly detection, and user click streams for sequence modeling. ML approaches for temporal data range from classical statistical models like ARIMA to deep learning with RNNs, LSTMs, and temporal transformers. A critical rule is to always split chronologically to avoid data leakage. Let's consider a demo showing how the same customer purchase information can exist in two different formats: structured data in a SQL table or unstructured data embedded in a support email. The format entirely changes the required pre-processing path. We now move to multimodal data. This occurs when a single problem requires multiple data types simultaneously, which makes the problem qualitatively harder. Multimodal systems are needed when one data type isn't enough. Examples include self-driving cars, which fuse images, LiDAR, and map data; medical diagnosis, combining images, lab values, and clinical notes; and e-commerce ranking, using product photos, text, and click history. Self-driving cars are a key example of a multimodal system, fusing vision from cameras, 3D point clouds from LiDAR, structured map data, and time series data from IMU and GPS sensors. Each modality requires a specific processing architecture. Multimodal systems are hard due to technical challenges like aligning different data embeddings into a shared space, dealing with asynchronous sampling across sensors, and managing modality imbalance where models favor dominant data types. Fusion strategies like cross-modal attention are often required. We'll conclude with a decision framework, a practical flowchart for identifying the type of any new dataset and understanding the constraints that follow. This flowchart can be used as the first step in any new ML project. When in doubt, treat the data as the harder type. It's easier to simplify a pipeline than to rebuild one after discovering hidden structure. This map summarizes the journey from data type to final algorithm, highlighting the required preprocessing and key pitfalls for each. Use this as a reference when starting any new machine learning project. The reality is that most production data is a messy hybrid. The skill is recognizing hybrid data and decomposing it into components that each receive the appropriate, tailored treatment. Hybrid data is the norm, not the exception. Real production datasets are composites, like AN commerce order record containing structured IDs, unstructured review text, and time series timestamps, all needing different pipelines. When dealing with hybrid data, apply the decomposition strategy. Decompose into atomic types, route to specialized pipelines, represent each type as a feature vector, and finally, fuse the features for the final model. You can now classify any dataset, map its type to the correct algorithm, explain feature extraction for unstructured data, recognize multimodal problems, and, most importantly, ask the right first question in any ML project. We encourage you to join the conversation. What type of data do you work with most in your current role? Share your production war stories, the hybrid nightmares and the schema drift incidents in the comments. Coming up next in Module 2, Episode 3, we dive into cleaning and preparing data. We will cover strategies for missing values, outlier detection, feature engineering fundamentals, and avoiding data leakage.